Having looked at number of thermodynamic quantities, especially the 4 laws, including the 0th law of thermodynamics, we have learned about thermodynamic potentials, equation of state. We have looked at the properties of classical ideal gases, the concept of entropy, and that at equilibrium it is the maximum value. We have to close our discussion on thermodynamics, but before that we will do some of the important things about thermodynamics which are important for a thermodynamics course, and some of them are not so very relevant to the statistical mechanics course, but yet we want to do them for completeness. Thermodynamics was initially developed for devising thermal engines and refrigerators, and these examples are car engines and refrigerators, steam turbines and so on. And if you look at the schematic diagram of a steam engine, there is a heat bath which is operating at a temperature Ta, and it is connected to an engine which is given by E. So, this E is drawing a heat Qa from this bath Ta maintained at Ta, and it is rejecting heat which is Qb, which is going into another bath, let us call it as Tb. And so, the work done is given by Qa minus Qb, that is the difference in the heat. So, it is just dq, which is Qa minus Qb here. So, Qa and Qb are indicated, which are respectively the heat taken from the bath at Ta and rejected to the bath at Tb. So, this is Qa minus Qb, and the way one defines the efficiency of this engine is the ratio of the work done divided by the input heat, that is Qa. And we know that the various statements of second law of thermodynamics, they demand that the efficiency, the maximum efficiency has to be 1, and it cannot actually attain an efficiency 1 in all practical cases. So, eta the efficiency should be less than equal to 1, and in practical cases less than 1. So, the second law also demands that the change in entropy should be positive, which means the change in entropy for the heat bath above, or which is maintained at Ta, is minus Qa by Ta, whereas the entropy associated with the heat bath below, which is maintained at a temperature Tb, is Qb divided by Tb, and this delta S has to increase, and for a reversible process it is only the equality sign would hold, and that would give the delta S to be greater than 0, and this quantity which is minus Qa by Ta plus Qb by Tb equal to 0. Now, one can easily calculate what the efficiency is. So, efficiency is given by W over Qa, which is what we have seen here, and then one can take this equation and then find out the relation between these. So, this is Qa by Ta equal to Qb by Tb. We are taking the equality sign just to have a relationship between them, and so this is gives you that Qa is equal to or Qa by Qb is equal to Ta by Tb. Okay. All right, and one can put them here, and one will get that the efficiency is given by there is just one line that you can do. So, efficiency is given by eta equal to or less than equal to 1 minus Tb by Ta, and this is called as the Carnot efficiency, and this gives you the maximum efficiency of an engine, okay, and this is called as the Carnot engine, this Carnot engine is the name of a person, and for most efficient engines delta S equal to 0. So, this equality sign would hold in the efficiency, and so it differs from the maximum possible efficiency by this ratio T b by T a. So, if you want to know how to make a Carnot cycle or a Carnot engine with an ideal gas, then it has to go through this in this PV diagram through all these processes which are shown as A to B and then B to C, back to C to D, and then D to A. In this closed cycle you have to operate, and where A and B are isotherms and C and D are isotherms as well, because they are at a given temperature, which are shown as T a and T b, where the bath temperatures that were shown in this Carnot schematic diagram. So, B to C, that is this B to C that you see here, this one is B to C, is an adiabatic process, and D to A is another adiabatic process. So, a classical ideal gas will have to be taken through this closed cycle in order for this engine to operate. Okay. So, let us get into another topic that is often taught, and is called as a Maxwell's relations. And please do not make a confusion with Maxwell's equation in electrodynamics. These are called Maxwell's relations, and so let me just write down Maxwell's relations in thermodynamics. And let me do it along with you. Again, we start from this equation combining the first and second laws of thermodynamics. So, du equal to Tds minus Pdv, that is combining the first and second law, and we are not connecting it to a bath. So, that there is no mu dn factor at this moment. So, here of course, the assumption is that u is actually a function of s and v, which are the independent variables, and t and p are actually dependent variables. So, we can write this as a del u del s v and a ds plus del e as del u del v. So, this del u del v and s and a dv. Okay. So, this is if you take a sort of differential, then this will be a du, and this is done earlier. So, there is a del u del s at a constant v ds and plus a del u del v at a constant s and a dv. So, we identify from here that we have this as T, the temperature, which is del u del s, and the pressure is equal to a minus del u del v. This has been done, but let me still do that. So, this is equal to del u del s at a constant v, and P is equal to minus del u del v at a constant s. Okay. So, these are known to us. Since these are exact differentials, this du is an exact differential, what we do is that we take a del del v of this thing, which is del u del s at constant v, and this del del v is taken as a constant s, and we take a del del s of the other term, which is del u del v at a constant s, and this is del del s is taken at a constant v. So, this is nothing but t. So, we will write del t del v at a constant s, and we take a del del s at a minus. So, this is a minus p. So, this is a minus del p del s minus of del p del s and at a constant v. So, what I did was that because these are exact differentials, we have taken a volume derivative here with respect to volume and this with respect to entropy, and we arrive at a relation which is equal to del T del V at a constant S equal to minus del P del S at a constant V, and this is known as one of the Maxwell's relation. Okay. And there are other like 4 Maxwell's relations which we are going to derive. Let us look at something very interesting here. If you look at the first line that you see here, there is really an amazing thing about mathematical feature that is embedded into this first and second law. So, when u is expressed in terms of the particular pair of variables which are, as you see, S and V, and so the coefficient of the differentials which are coefficient of these differentials like these ones, they denote the natural variables which are T and P for which are dependent variables rather, or natural variables or dependent variables for this the coefficients would denote the dependent variables. So, this is something very interesting, and so once again I just repeat this, that the internal energy is a function of S and V. Now, when you write down du, that is take an exact differential and you write it as 2 terms which are shown here, the coefficient of these 2 terms actually are the other set of variables which are the dependent variables, namely the T and P, and as you know earlier that S and V are the independent variables. Okay. Now, we shall use this generating relationships between the partial derivatives, and these will give rise to the Maxwell's relations that we get, and we will use different thermodynamic potentials in order to get these relations or this Maxwell's relations. Okay. So, let us take the next one as V to be or rather this is the Helmholtz free energy. So, Helmholtz free energy is nothing but F equal to U minus T s, and as you know for open systems there will be a minus mu n factor which we are not writing. So, dF is equal to d of u minus T s, which is du, sorry let me write it as capital U. Please follow certain notations that you are familiar with. Mostly the internal energy is written with U, but in some texts or articles or books even you find that as written as capital E. We will continue with this notation that we have introduced earlier, and there is a minus d of T s, and this is equal to a du minus a TdS minus an SDT, okay, because we are taking exact differentials. Now, we can write down du as the TdS minus PdV, which is combining the first and second law. So, that first term is du TdS minus PdV, and then we have a TdS and then we have a SDT. Okay. So, clearly the TdS cancels out and we are left with just minus PdV and minus SDT. So, we will follow the same thing that we have done earlier, and we would write f as a function of Tv. So, this will give us that df is equal to del f del t at a constant v dt plus del f del v at a constant t d v and so on. So, now we can again do a comparison between the two, and the first term is actually the second term. So, P is equal to, P is nothing but a minus of del f del v at a constant t, and S is nothing but a minus of del f del t at a constant v. Now, what we do is that we will again take a derivative with respect to volume and pressure. So, we know that P is equal to minus del F del V at a constant T, and S is equal to minus of del F del T at a constant V. Now, we take this del S del V at a constant T will be nothing but del P del T at a constant V. Okay. So, what we do is that we take a derivative. So, let us take this first one. So, it is a del P del T at a constant V will be a minus del 2 F del, or rather we can just simply write it del T of del F del V at T, and similarly that is the first one, and we have a del S del V at a constant T. So, this is taken at a constant V, and this will be minus again del V of del F del T at a constant V, and the whole thing is at a constant T. Now, you see if you look at this inside the square bracket, you see there is a del F del T of del F del V, and there is a del V of del F del T. Now, you can interchange the order of this taking derivatives, and you see that they are same, and because they are same we get another relation, which is the second Maxwell's relation. Let us call it as S del V T equal to del P del T V. Let us look at the next one. The next one will use the enthalpy. And enthalpy is again defined as H equal to U plus P V. They all are done in the similar fashion. So, this is equal to, we take a dH, and dH is equal to d of U plus P V, which is equal to du plus P dV plus a V dP, and once again we use du equal to TdS minus PdV, that is combining first and second law. So, this will be TdS minus PdV plus a PdV and plus a VdP. Clearly, the PdV will cancel out and we get a TdS and VdP. Once again, this H being a function of, this you can write down dH as this TdS plus VdP, and H is a function of S and P, and we can write down this dH. So, let me write it here. H is a function of S and P, and once again you can do a dH, which is equal to a del H del S at a constant P ds plus a del H del P at a constant S dP. Now, you see that there is a ds here. So, this is equal to TdS plus a VdP. Now, you see that there is a ds here. So, the coefficient is T is equal to, this tells you that if you compare these two equations, then T is equal to del H del S at a constant pressure, and your V is equal to del H del P at a constant entropy. So, now what we can do is that we can take a derivative of temperature with respect to pressure and take another derivative of volume with respect to entropy, and we will get the equality sign for this. So, exactly following the earlier method. So, we have a del T del P at a given S is equal to a del V del S at a given P. So, this is the third Maxwell's relation, which is obtained from the enthalpy, and finally, we use the Gibbs free energy for the next one. Okay. So, this is written as G is equal to H minus T s, or is equal to U plus P v minus T s, and so d G becomes equal to d U plus a P d V plus a V d P minus a T d S minus a S d T. Once again, using du equal to T d S minus P d V, there is a plus P d V and there is a plus V d P, and there is a minus T d S and a minus S d T. So, clearly the P d V's will cancel and the T d S would cancel, leaving us with a V d P minus a S d T, and it is easy to see that your G is a function of T p or P t. So, G is a function of T p, and then again we write this down as d G equal to del G del T P d T. Is the same thing repeated over and over again with different energy functional, and then there is a del G del P at a constant T, and this is a P. Being an exact differential, we can take another double derivative for the first one with respect to P and the second one with respect to T, and they would be same. And once we actually compare with the one that is here, so if you call this as equation 1 and this as equation 2, which were there everywhere earlier. So, we can get a del S del P T is equal to a minus del V del T P. Okay. Just following the same things, we get 4 Maxwell's equation. Let me just show you. So, one is del T del V at a constant S equal to minus del P del S at a constant V. The second one is del S del V at a constant T equal to del P del T at a constant V. Then it is a del T del P at a constant S equal to del V del S at a constant P, and these del S del P at a constant T equal to minus del V del T at a constant P. What you have to remember, you do not have to remember all this equation, but what you should remember is that we are using all the thermodynamic potentials, internal energy, Helmholtz free energy, enthalpy and Gibbs free energy, and arriving at the relationships by using repeatedly the combination of the first and second law. Okay. So, there are some interesting mnemonic devices, or mnemonic device is the one that helps you to remember these relationships, and they are written as in a sort of square fashion. There is something interesting. So, it is U and a minus V and a F, and these are S and minus T here, and you have a G here and you have a P here and you have a H here. Okay. So, you are writing various quantities, thermodynamic quantities, including the potentials and other intensive and extensive variables. So, these free energies are written at the corner. So, if you start from the right corner, it is, if the way to remember it is that this is like they are alphabetically arranged. So, it is F, G, H and then U. So, this is how you go from here, and the two extensive variables are kept at the two middle positions on the first row, and on the left middle of the left column, and we put again the two intensive variables which are with some signs which are important, because to get these Maxwell's relations correct. So, they are minus t and p. So, if you really start from this like this and then you go like this and then you go like this and then you go like this and then you come like this. Okay. So, the direction is like this. So, you can follow this path, and you can just get these relations like all these following this minus. So, there is a minus 1 into del S del P t is equal to a minus 1 into a minus 1, which gives you a plus, and a del V del t p, and so on and so forth. This is the relation that we have seen here, del S del p t minus del V del t p. So, this minus sign is interchanged. So, this is that S and P. So, del S del P, you come from here to here, and then you have del V del T, and these negative signs are arranged, and this is just a way of remembering this for Maxwell's relations. They are interesting by themselves, but if you remember them, there is nothing, there is no need for such a device. All right, let me carry on little more with the discussion on the thermodynamic potentials, and the reason for doing that is that we will introduce something called as a Legendre transformation. And what this is? It makes us transform from one thermodynamic potential to another, and that means that these potentials are not independent, which I think you understand very well from the form, but how they are connected and what is the relationship between them, one can make a formal platform in order to explain this interrelationships between different thermodynamic potentials using a Legendre transform. And we will look at sort of in brief what Legendre transformation is, but let me try to sort of give you a feeling that what we are trying to do. So, we take this u to be a function of S, V and N, which we have already seen. This is for an open system, and particularly we are going to make a distinction between open system and closed system or isolated system. In fact, we will just see in a while the difference between them. And so, this is du equal to TdS minus PdV plus a mu dN. Let us call this as equation number 1. Okay. This is combining first and second law, where T is given as del U del S V N, P is nothing but minus del U del V S N, and mu is del U del N and S and V. Okay. So, these are the relationships of all these the coefficients in terms of the differentials. So, the temperature, pressure and mu all are intensive variables, and they are expressed in terms of the extensive variable. And similarly, if we now convert it into S, and in fact, S, the entropy is an important thing, not only that we have seen through second law of thermodynamics, but it is an important thermodynamic potential, especially for the closed system. So, we can write down S as a function of U, V and N, use S as a thermodynamic potential. This will give us a ds is equal to again a 1 over T du plus a P over T dV and minus mu over T dN and these are the quantities that you get, and we will sort of this, let us call it as equation 3. And if you again open it like write ds equal to del s del u at constant V n into du and so on and so forth, and then okay, let me write that down just to avoid any. So, there is a del s del u at a constant V n and a du plus a del s del V at a constant u n dV plus a del s del n at a constant u and v into dn, and compare between equation 3. So, you have a du here, the first term, and the coefficient is 1 over t. So, del s del u is equal to, so 1 over t is equal to del s del u v n. P over t is nothing but equal to del s del v u n and mu over or minus mu over t equal to del s del n u v. Okay. Let us call this as equation 4. Okay. So, these are nicely defined, just like we have used u to be a function of s v n, we can use s as a function of u v n, and there is an equivalent description using everything that we are aware of. Okay. So, this equation 1 and 3, these are called as the equation of state of the system. Equations of state. Okay. So, u and s can be obtained by integrating equation 1 and 3. Okay. And sometimes if you look at equation 3, which is that for the ds, it is more useful because the equilibrium state of a system is a state of maximum entropy. So, ds is maximized, and that is the reason that we sometimes we find more this equation 3 to be more useful than equation 1. Nevertheless, I mean this they are called as the equations of state. Now, these extensive variables such as u, v, s, n, etc., they of course vary with the size of the system, as you know. They are convenient while discussing closed systems or isolated systems. So, I write useful in discussing isolated systems because they attain constant values. Okay. However, when you have a system connected with a heat bath or an open system, or there are diathermic walls that we have studied earlier, then these extensive variables are not very useful. Rather, one actually it is easier to talk about the intensive variable, and in any case the intensive variables are easier to control, and the intensive variables are nothing but this T, P, mu, etc. of the system. Okay. So, what we look for is a transformation from S or U to another potential and which is a function of these T, which is nothing but equal to del u del s at constant V, or P, which is nothing but minus del u del V at a constant S and N and maybe all that. So, V and N and this S and N and things like that. Okay. So, we look for a transformation of this change in thermodynamic potential from either S or U to these a function which is a function of not the extensive variables which are U, V, S, N, but they are functions of the intensive variable which are T and P. Because you see what will happen is that in the event that a system is connected to a bath, say a heat bath, it will eventually come to an equilibrium at a given temperature T, which is an intensive variable, or there will be a pressure which one can maintain at a constant pressure by adjusting the piston at a given position. Okay. So, this is done by a general method called as the Legendre transform or transformation. Okay. This is an important thing. So, let me quickly sort of tell you what Legendre transformation is, so that it is easier to understand. The idea is simple. We go from one variable to another variable, that is all. Okay. So, let me write down some f which is nothing but f of x. So, we take a function which is only a function of x, and what we do is that we would go from this f of x to another function which is g, and that is a function of another variable, we can call it x prime or we can call it g p. So, that the nature of the function remains same, but while f is solely a function of x, g will be a function solely a function of p, and now we are doing it for one variable, but we can do it for multiple variables just following the same method that we are going to discuss here. All right. So, we have a df which is equal to a df dx into dx. So, or del f del x, we are just writing it because it is just a one variable. So, we can write it as df dx. So, this is equal to p of x into dx, okay, where of course, p of x is equal to the derivative of the function. Okay. Now, consider this graphically. So, let us have a function, arbitrary function like this. Okay. So, this is f of x and you have x. Now, take a point x 0, say here. So, this is x 0. So, identify the point where this is f of x 0. So, I take a point which is x 0 f of x 0, this point here, okay. And now, draw a tangent. Let me try to do it. It is not very good, but you know what is happening. So, I draw a tangent t of x. So, I write t of x is the tangent at x 0 f of x 0 and so on. Okay. And this cuts the y axis at g of x 0. Okay. And so, this is all what we need. And so, this T x has some equation which we are going to write in just a while, and this T x, as I said, this cuts the y axis, which means at x equal to 0 at this value, and will show that. So, a priori will show that g of p is purely a function of p. And this is the Legendre transform or transformation that we are talking about. Okay. Let me write down the equation for T of x. So, T of x, this line that you see is a tangent line, it is f of x 0 plus a f prime at x 0 x minus x 0. This elementary, this trigonometry that we have or rather geometry that we have, not trigonometry, geometry. So, T of x is equal to f of x 0 f prime x 0 x minus x 0. The intersection with y axis is g is equal to t at x equal to 0. Okay. So, this g at x 0 is equal to t at x equal to 0. Okay. All right. So, so g of x 0, let me go to the next page. So, g of x 0 is equal to f of x 0 minus x 0 f prime of x 0, correct. So, this is a equation that we know. Now, this is at a given point x 0, but it can be at any point. So, we can generalize it to any point, that is g of x is equal to f of x minus x p of x. Okay. If it is true at x 0, which is an arbitrary point anywhere on the curve, then it is true for any variable x. And just to remind you that, so let us call this as equation 1, and p of x is nothing but df dx. Okay. Now, taking a differential with respect to 1, so I have a dg which is equal to a df, just eliminating this x dependencies, minus x dp minus p dx. This looks more like the thermodynamic differentials that we were taking. So, let us call this as equation 2. Now, introduce df is equal to p dx, okay, which can be seen from here. So, dx is or df is equal to p dx. Okay. So, we can write down this as dg, it is equal to a p dx minus a x dp minus a p dx. Clearly, this cancels out. So, dg equal to a minus x dp. So, from the discussion that we have, now you see that g is a function of p only, okay, because p is the independent variable, x is a dependent variable. So, g is a function of p only, and if you want to actually calculate the explicit form of g, that is possible. So, we will use p is equal to f prime, and it is possible to define g unambiguously and a function of solely on p if this quantity exists, which is f prime of x, inverse of that if it exists, because if you see that del f del x is p. So, the inverse of this is 1 over p. So, that would exist if only p exists, which means that it does not blow up, which means that this quantity does not blow up. So, this tells you that x is equal to f prime p and inverse of that, and so we can put it down into equation 2 or rather equation 1 and write g of p equal to f of f prime of p inverse, which is f of x, because x is equal to this thing. So, let me, if you want, I can put another bracket just to. So, this is a function. So, that is f of x. that is f of x in 1, and a minus, that is the second term, is f prime of p inverse of that and multiplied by p, which is there in the second term. So, this is the second term in equation 1. So, this is the first term and this is the second term. Okay. Very well. So, that tells you that you can see it very clearly that G is purely a function of P. So, G P is solely a function of P, which means that that will only be true if P is not equal to 0, okay, which makes sense. Let me give you a simple example just to make this point clear. Consider f of x equal to x square. So, f prime of x is equal to 2x, which is according to our convention it is equal to p. So, g of x, putting into the equation 1, it is equal to x square minus px. Now, we have to eliminate x using, so eliminate x using x equal to p by 2, which is coming from this equation C f prime equation above. Okay. So, if you do that, then your f prime p, the inverse of this becomes equal to x, which is equal to p by 2, and then the g of p is equal to 1/4 p square, because it is x square the first term, and then minus px, that is half of minus half of p square, because x is p by 2 and then multiplied by p. So, it is p square by 2 and this is equal to minus 1/4 p square. So, now we got g solely a function of p, and you can see it easily that dg, this is equal to a minus half p dp, which is nothing but minus x dp, which is correct, which is what we have just got earlier. Okay. So, this is for any arbitrary function, and as I said that this Legendre transformation can be generalized to more variables. Okay. Let us just see this for the thermodynamic potential. So, let us say the free energy and internal energy. So, Helmholtz free energy. So, F Helmholtz free energy and internal energy. So, one of them is x and one of them is p. Okay. So, F is equal to u minus Ts, which is nothing but minus Pv plus mu n. So, for the internal energy we of course are familiar. Now, we are talking about not a closed or isolated system, we are talking about an open system, and this is very important because we have these mu that needs to be considered now. And so, du is equal to Tds minus Pdv plus a mu dn, and we can so this is for the du, and for the df it is equal to du minus s dt minus Tds, and again we use du equal to Tds minus Pdv. So, minus s dt minus Tds, this will cancel and df becomes equal to, so this is a minus and there will be a plus a mu dn, which would be there mu dn, and this will be df would be equal to minus s dt minus p dv plus a mu dn. So, what we have achieved by this, so what I want to stress upon is that f and u are connected by Legendre transformation. So, while u was a function of s, v and n, f is a function of t, v and n. So, we have eliminated s. Because s is not a useful quantity when you have connected it to a temperature bath or a heat bath, and it is a sort of a non isolated system, it is an open system, and then s is I mean it is more convenient to talk about the TVN in replacing s by t, which is a intensive variable. T is an intensive variable, and indeed when you keep a system in contact with a bath, the temperature becomes a constant or remains constant, whereas it is difficult to talk about entropy. So, the whole idea is that all these thermodynamic potentials that we have talked about, F, G, H, U, etc., they are useful in their own rights, and sometimes one is more useful to talk about than the other. And here in a limited way, of course, you see that u and f are functions of multiple variables. So, this Legendre transformation that we have taught on a sort of a general sense, that needs to be, we have done the Legendre transformation in a specific sense, it needs to be generalized to larger number of variables. Nevertheless, the central message is that all these thermodynamic potentials are connected, or they are related to each other by the Legendre transformation. We will stop here with the thermodynamics part, and would carry on with the statistical mechanics, the beginning of statistical mechanics. Thank you.